Let us try to understand what equilibrium is through a simple observation. Look at the closed container with a small amount of liquid bromine. What do you observe? You observe that some of the liquid bromine is evaporating to an orange vapor, and slowly the vapor becoming thicker. After some time, you can see that there is no change in the intensity of the vapor anymore, and also that a small amount of liquid bromine is left in the flask. How do you explain this? Here's the explanation. All the molecules in a liquid do not have the same kinetic energy. Some molecules at the surface of the liquid that possesses a relatively higher kinetic energy escape from the surface into the vapor phase. When the air inside the container is saturated with vapor, the molecules in the vapor phase condense to liquid as fast as the liquid evaporates. After some time, the number of molecules evaporating from the surface in a given time becomes equal to the number of molecules condensing on the surface during the same time. At this stage, equilibrium is said to have been established between the liquid and the vapor phase. This is why we see that the color of the vapor in the flask does not change. Thus, equilibrium may be defined as a condition in which two opposing tendencies balance one another. The equilibrium of liquid bromine with its vapor may be represented as Br2 liquid in equilibrium with Br2 gas. The pair of half-headed arrows indicates that the two processes, evaporation and condensation, are occurring simultaneously. At equilibrium, the rate at which the particles move from the liquid to the vapor phase will equal the rate at which the particles move from the vapor phase to the liquid. In this situation, the concentration of the vapor particles in the air space will be constant even though there is movement in both the directions. This equilibrium is, therefore, known as dynamic equilibrium. The opposing tendencies of a reversible change continue to take place with equal rates simultaneously at the equilibrium stage also. Hence, the equilibrium is called dynamic equilibrium. Equilibrium can be established for both physical and chemical processes. At the equilibrium state, if there is a change in the physical state, the equilibrium is called physical equilibrium. The important aspects of equilibrium involving physical processes can be understood by studying some phase transformation processes, such as solid-liquid, liquid-vapor, solid-vapor. Let's see solid-liquid equilibrium. Ice in equilibrium with water in a perfectly insulated thermos flask at 273 Kelvin and at atmospheric pressure stands as a perfect example of solid-liquid equilibrium. For this equilibrium, you can see that the temperatures as well as the masses of ice and water remain constant. Why is this so? Ice-water equilibrium is a dynamic equilibrium, where the number of molecules going from ice into water and the number of molecules going from water into ice are equal. As the rates of transfer of molecules from water to ice and from ice to water are equal, there is no change in the masses of ice and water. Since the system is insulated, no exchange of heat between the system and the surroundings is possible, and hence, the temperature remains constant. The equilibrium for this phase change may be written as H2OS in equilibrium with H2OL. It is important to note that ice exists in equilibrium with water only at a particular temperature and pressure. Thus, for any pure substance at atmospheric pressure, the temperature at which the solid and liquid are at equilibrium is called the normal melting point or normal freezing point of the substance. Let's now look at liquid-vapor equilibrium. Water in equilibrium with vapor in a closed vessel serves as a classic example of liquid-vapor equilibrium. Let's understand this through a simple experiment. A small amount of water is taken in a closed vessel to which a manometer is attached and left undisturbed for some time. After some time, you can see the slow increase of the mercury level in the manometer and the final attainment of a constant value. Did you also observe that there is a decrease in the volume of water in the vessel? How do you explain this? In the beginning, there was no water vapor inside the vessel. As water evaporated, the pressure inside the vessel increased, which was indicated through the rise in the level of mercury in the manometer. After some time, the level of mercury in the manometer remains constant, indicating that a state of equilibrium has been attained between water and water vapor. The molecules of the vapor in their movement collide with other molecules, with the walls of the container as well as the surface of the liquid. When some of the molecules with less kinetic energy come closer to the liquid surface, they get attracted to the surface. This process is called condensation. At any given temperature, evaporation and condensation take place simultaneously. After some time, the rate of evaporation becomes equal to the rate of condensation, and then liquid-vapor equilibrium is established. The pressure exerted by vapor over a liquid when it is in equilibrium with the liquid at a given temperature is termed as the vapor pressure of the liquid at that temperature. Water exists in equilibrium with its vapor at atmospheric pressure in a closed vessel. Thus, for any pure liquid at 1 atmospheric pressure, the temperature at which the liquid and vapor are in equilibrium is called the normal boiling point of the liquid. Let's look at solid-vapor equilibrium now. Some solid substances directly undergo a phase change from solid to vapor without the intermediate liquid state. This is called sublimation. Observe the solid iodine placed inside the conical flask and fitted with a cork. You can see the vessel getting filled up slowly with violet vapors. Have you observed that the intensity of the color has become constant? At this stage, we can say that an equilibrium state has been attained for the system. At equilibrium, the solid iodine sublimes to give iodine vapor, and the iodine vapor condenses to give solid iodine. The equilibrium can be represented as I2 solid in equilibrium with I2 vapor.